Hey everyone, so this video you're going to be watching today is going to talk about position versus time graphs, velocity versus time graphs, and motion maps. So with this video, I'm going to go through a couple different slides. I'm going to be talking about some things, drawing some things, and you should hopefully watching this, the only way you're going to be watching this is in the Educanon app. So occasionally, just to check your understanding kind of that you're picking up on the things I'm talking about, there'll be some multiple choice questions you're going to answer. So that's just some accountability for you that you actually did watch the video. And then I can also get a good feel of where everyone in the class is with the information that we are talking about. Now, a couple of things I'm obviously going to be drawing, so you'll see those kind of show up on the screen as I'm talking. But something else that you might see as it comes up will be different kind of laser pointers. I can use laser pointers here to kind of highlight certain things I talk about. Also, you may see, including laser pointers, they also have lightsabers, which are pretty cool to act as laser pointers too. I know what you're thinking, this class gets cooler and cooler every day. So those are some of the things we'll be talking about, some of the things you'll see on the screen, and then just answer those questions when you do get to them. Now, the couple things that you're going to need for this are your constant velocity unit plan, which is that green page that I gave you the other day in class on Monday, and then something to write with, pen, pencil, whatever you want to write with. Then a scrap sheet of paper. It can be notebook paper, graph paper, computer paper, whatever you need, just to draw the couple things that I might be drawing as we go through this. Now, my goal by the end of this video is that you should be able to write a written description of motion based on a graph or a motion map. Also create a velocity time graph from a position time graph, and the kind of reverse of that, so going from a velocity time graph to a position time graph, and then also creating a motion map from a written description or a graph. You'll be using those kind of skills tomorrow in the motion detector lab. So the first thing we're going to talk about is just describing motion based on a position time graph or another graph. So we talked a little bit about this at the end of class today after we worked through that worksheet. So we kind of have hopefully a good grasp of this right now. But just in case, just kind of hit it again. So if we're looking at a position time graph, let's just assume these are two cars kind of moving along a straight road. So if we're going to describe the blue car first, we could kind of look at that as the blue car is moving away from the starting position because we have a positive slope, and it's moving at a constant velocity. But it's moving slower than the green car because its slope is less steep. And then kind of describing the green car's motion, we could say that the green car is moving away from the starting position at a constant velocity, but moving faster than the blue car. So we want to kind of hit both of those ideas that both objects are moving at constant velocities, but one car is moving faster than the other. Now, the next thing you're going to do is answer a question kind of based on a graph I'm going to give you, and then answer the multiple choice question that goes along with it. Now, something we haven't quite talked about yet is going from a position time graph, so up at the top left, to a velocity time graph. Now, if you look down here on the velocity time graph, you'll see a couple things here. You'll see that we're looking at positive velocity right here, negative velocity down on this end of the graph, and this is our kind of zero velocity line, but also it's our time axis. So as time goes on, how is the velocity, where is it at in reference to that? But again, this axis also representing zero velocity here, positive and then negative velocities. So if we're going to draw the green car here, we know that the green car, we said before, is moving away from the starting position, and it has a positive slope, so it means it has a positive velocity. So we could go ahead and draw that on the velocity time graph. It might look something like that. So it has a positive and constant velocity. That's how we show that on the graph. Now, we said in the description before that the blue car is moving slower, so we're going to want to put that lower on this axis to show that the object is still moving. This car, the blue car, we can say again, is moving at a constant velocity, but again, it's moving slower than the green car, and that's kind of how we would show that. Putting both in the positive region of the graph, but then showing them both as constant. Now, if we go to this graph, so a little different here. Now we have a blue car and a green car again, so let's look at the blue car first. Blue car again has a positive velocity, it's constant again. So we'll go ahead and put that somewhere in this region here because it's still moving kind of slow. Ignore that bump in the line, it should be a pretty straight line. But now if we look at the green car, we can see that its slope is now negative, meaning it's going to have a negative velocity. It's moving in the opposite direction of the blue car, or it's moving towards the origin or the starting position. But we can see that its slope is a lot steeper than the blue car's, so therefore it's moving faster than the blue car. It's just moving in the opposite direction. So we want to put the green car kind of way down here to show that it has a high speed, so that high value for its velocity, but that it's negative, meaning it's moving in the opposite direction. So we can still show that one car is moving faster than the other, even on this velocity time graph. Now go ahead and answer the questions based on creating a velocity time graph from a position time graph. Now the next thing we're going to talk about is kind of the reverse of what we were just talking about. So in this case, we're going to be creating a position time graph from a velocity time graph. So if we look at our velocity time graph kind of up here in this region, we see that we have two cars again, a blue car and a green car, both moving with positive velocities, and we can see that the blue car is moving faster than the green car down here because it's higher. It's a higher velocity up here. So now we just need to show that on a position graph. So we need to show that they're both have positive velocities, but the blue car is moving faster than the green car. So one way we could do that would be to show blue with a really steep slope, and then green kind of coming in that same direction, but with a slope that's a little less steep. Something like that. Now you could kind of change it up a little bit qualitatively as far as how steep they may be, but just making sure that the blue line or the blue slope is steeper than the green slope. Another kind of look at that, we have the blue car and the green car again, but now the green car down here is moving with a constant, or negative velocity, still constant but negative. So we would need to kind of show that on the graph. So along with that, the blue car is still moving faster than the green car because it's higher up on its axis away from zero. The green car is still not that far away. It's just one's positive and one is negative. So for example, we could draw the blue car again with a very steep slope. And then the green car, it could kind of vary. We could start it wherever we would really want. It's moving towards zero. So we might want to start it here with kind of a less steep slope. So again, it's kind of arbitrary. It doesn't really matter where you start the green line. We just need it to show that it's kind of moving down in this direction towards zero. It doesn't necessarily have to be anywhere specifically right now because it is just a qualitative graph. Some of the numbers aren't our biggest concern right now. It's just kind of getting this idea down. And now go ahead and answer the questions that have to deal with creating a position time graph from a velocity time graph. Now the final idea we're going to talk about is creating a motion map. So there's just one other way we can represent the motion of objects. We'll use these throughout the rest of this first semester especially. But so let's, for example, say Mr. Weissong, myself, walks from his classroom to the stairwell at a constant velocity in 6 seconds. We'll assume that my classroom is the zero position on this number line down here, and I have the box there just kind of covering up the motion map portion of it right now. But down here's the zero position, so then I'm going to move towards the class, the stairwell, at a constant velocity in 6 seconds. Now, I would draw the motion map. It would look something like this above here. We're going to go over the rules, but you can see that kind of we have these arrows, we have these dots that all kind of represent different things. So you can see a smaller version of the motion map I drew up there. And then the key thing is, so again, it was Mr. Weissong walks from his classroom to the stairwell at a constant velocity in 6 seconds. So the dots represent position. So these black dots here represent position and equal time intervals. And we're always going to assume that each dot is 1 second has passed. So here would be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and then 6 seconds. So I've walked to the stairwell at a constant velocity. And the arrows kind of show that which direction I walk, so they're all pointing to the right. I never changed direction. And then the length of those arrows represents how fast I'm moving. So my, in this case, I don't really have a change, and so I can make the arrows as long as I want. But we want to show them all kind of being relatively the same length because I am moving at a constant velocity. And if you wanted to add lines here, like kind of congruency lines to show that these are all supposed to be the same length, meaning that I'm moving at the same speed the whole time, you could do that. And then obviously if I would change speeds using different congruency lines, like putting 2 lines instead of 1, something like that. Now one thing I didn't really show, but I'll show in the next example, is that when an object is stopped for several seconds, we're going to draw multiple dots at the same position. And then make sure that your sequence of arrows has just kind of a logical flow to it. And we'll see that in the next kind of situation. But go ahead and write down these kind of criteria on your green sheet so you have them with you at all times from now on. This is the big takeaway kind of from this video that I would like you to write down on that green sheet. So we're going to look at an example of a motion map. And draw this kind of looking at all kind of that criteria that you have written down on your green page from the previous slide. So Mr. Weissman walked from his classroom to the stairwell at a constant velocity in 6 seconds, stops for 3 seconds to talk to another teacher, then realizes he forgot something in his classroom and walks back to his room in 3 seconds at a much faster, but still constant velocity. So I'm going to do my best to draw this. So if we look at this situation, the first part of my motion map where I walk from the classroom to the stairwell is going to look pretty similar to the one I had before. So I'm going to want kind of 6 dots in here to show the 6 seconds that passes, and they might not be completely accurate as far as the distance apart that they are. But then again showing, oh wow, got rid of the dots there. That's not good. Let's draw a little smaller line. So drawing it away from the dots, again trying to show that they're all the same length, meaning I'm moving at a constant velocity. And there we go. So I move away from my classroom at 6 seconds. Then you kind of see that there. So I have those. If you want to add congruency lines, you could to show that the arrows are all the same length. And then it says that I stop to talk to another teacher for 3 seconds. So this is where we're going to stack those dots. 1, 2, 3. To show that I was stopped for 3 seconds. I'm at the same position. So you kind of see here I'm at the same position, but I'm stopped. So obviously I'm stopped. Time is passing, but I'm not moving. But then I realize I forgot something, which always tends to happen. So that next second there, so 1, 2, 3 seconds, and I'm going to be back kind of at my classroom. But I'm going to walk at a much brisker pace. So I'd want to show this with my arrows being just a little longer than they were before. So it looks something like this. And again, showing these lines are supposed to be the same length, and then these lines are all supposed to be the same length. So I can kind of see that I've walked, and to kind of summarize here, so I walked towards the stairwell at a constant velocity. I stopped for 3 seconds, and then I start moving again back towards my classroom because I forgot something, but I move faster, so my arrows need to be a little longer than they were before. Alright, so you're going to answer a couple questions about motion maps, and then we're going to use all this information tomorrow to work through our motion detector lab. So thanks for watching, and I will see you all tomorrow.